Okay, I think we are live. Let me know if you can hear me. Let me know if you guys can hear me. And I let me know. Okay, I can hear myself. So I think you guys should be able to hear me. So yes, hi everyone. And today we'll be solving optimal binary search tree. Now this is a very interesting problem, to be honest. Yes. Nika. छोड़ दिया, हाँ. Awesome. Thanks, Madhukar. So today we'll be solving optimal binary search tree. Now, I'm not sure if you guys were able to solve this. It's a pretty interesting problem, to be honest. Uh, well, there are solutions online available. Definitely, you could have checked that out as well. But here I'm to discuss this solution again. So in case you haven't understood some parts, I'll try to make it simpler for you. So let's first start by reading the problem statement. So you are given a sorted array of keys, 0 to n minus 1. These are the search keys basically. You are creating a binary search tree, right? So a binary search tree contains some search keys. So you are given a sorted array of these keys, and you are given an array that is called the frequency array. This basically tells frequency of I is the number of times you are searching for key of I, right? So number of times you are searching for this key of I, that is given in frequency of I. You have to construct a binary search tree of all keys such that the total cost of all the searches is as small as possible. So there are many binary search trees. Like if you already know about binary search tree, I'm pretty sure that you know about that. So if you know about that, you must be knowing that there are many binary search trees possible for the given search keys. Generally, then after that, we use something called a balancing factor to balance the search tree and fix one of them or something like that. But here don't have a balancing factor with us. We can create any binary search tree, right? Now you have to create the binary search tree that has the minimum cost. What is the cost? A cost is basically defined as the level of the node into the number of times it is being searched for, that is the frequency. So basically, just consider searching for a tree, right? Okay, बहुत सारे comments खुल गया. 1 second. So yes, so let's come to this example. So we have 10, 12, and we have the frequencies to be 34 and 50, right? So this is one possible binary search tree. This is also binary search tree, right? So binary search tree only has one property, that is the left side or left subtree nodes should be smaller than the given node, and the right subtree node should be greater than the given node. That is the only condition for a binary search tree. So both of them are binary search trees. Now the problem is like that you are searching for keys, right? Like binary search tree purpose is to allow you searching on keys. So you are searching on keys. Now when you are searching for a key, you have to go to that node, right? So you have to minimize the total traversal or minimize the total cost that is involved. So let's say for 10 you are searching 34 times, 12 you are searching 50 times. So 10, 12, this way, whenever you are searching for 10, you are just visiting one node. So it is 34 into 1. But whenever you are searching for 12, you are visiting two nodes. You are starting at 10 and then you are going to the right child and you are getting 12. So your total cost is 50 into 2, because every time you are visiting two nodes. So this is the total cost 34 into 1 plus 50 into 2, which is 134. If you take the other variant of the binary search tree, that is 12, 10, in this case 12 is visited one time, right? When you are searching for 12, it is visiting only one node. So the total cost is 50 into 1 plus, for 10 it is visiting two nodes, 12, and after that it is going to the left child and we are getting 10. So 34 into 2, so 50 into 1 plus 34 into 2, so it's 118, right? So is this clear? Is the question clear with everyone? Can you just confirm if the question is clear with everyone, or if you have some doubts with this question? Just confirm if the question is clear with everyone. I'll take this example as well. But before that, like, is the question like overall, is it clear to you, or do you need some more explanation on the question? 10, 12, 20. So let's write it down here. We'll take this example. 10, 12, 20. So 10, 12, 20. And these are the keys. And what is the frequency? The frequency is given by given is 34,850. 34,850, right? 34,850. Okay, so for this, just think about all the binary search trees possible with these, right? So we can have like this 10 is the root node. After that we can have 12. After that, to the right child we can have 20. This is a valid binary search tree. This is a valid binary search tree, right? Because all the nodes on the right subtree are greater than the given search key. So 10 right subtree has 12 and 20, so both of them are greater. Similarly, 12 has 20, which is greater. So this is a valid binary search tree. What are some other possibilities? We can have 10, we can have like this 20, and we can have 12. So this is also a valid binary search tree, because in 10 the right subtree contains 12 and 20, both are greater. For 20, the left subtree contains 12, which is lesser, which makes it a valid binary search tree. Similarly, there can be what can be there? 12 can come on the top 10, and there can be 20, right? But again, like, this is not a valid binary search tree. If you write it like this, it is not a valid binary search tree, because 10 is smaller than 12 and it is coming on the right subtree of 12, so it will violate the binary search tree condition. So this is not a valid binary search tree. So this is one of the valid binary search trees. Again, 20 and you can have 12 and you can have 10, or you can have 20, 12, 10. So I think these are the possible values of the binary search trees, right? Now let's look into the cost for each of them. So for this, you have the frequencies given, right? So for this, the cost will be what? For 10, you are just visiting the root node, so 34 into 1, 34 times you are searching for 10. 12, you are searching 8 times, and you are just visiting two nodes, the root node and the 12. So 8 into 2, and you are searching 20 50 times, so 50 into, you are visiting 3 nodes, right? 10, 12, and 20. So you're visiting 3 nodes. So this is the cost: 34 plus 16 plus 150. That is something, right? I'm not computing. You can actually look into the values. I think the values might be given here. They are not, so that's fine. Again, here it's 10. Sorry, not 10. 34 plus 20 is done 2 times. 2 nodes are visited for 20. So 50 times it is called, and it will be 2 nodes plus 8 into 3, right? Because 3 nodes are visited for searching for 12. So that's basically 34 plus 100 plus 16. You can compute the value. Similarly, I will compute the values later, right? We'll definitely compute them, because I have to explain why it is smaller. So 12, 10, 20, what is the cost again here? The cost here will be, let's write it here. So it will be 8 into 1. 12 is visited 8 times, and only 1 node is visited here. So 12 into 1. Plus for 10, we are visiting 34 times, and we are visiting 2 nodes. 34 into 2. For 20, you are visiting 50 times, and there are 2 nodes you are visiting. So this will be the total number of calls, or the total cost, right? Here again, what will it be? It will be 20. So 20 is visited 50 times, right? Sorry, my bad. So 50 into 1 plus 12 is visited 8 times, so 12 into 2 plus 10 is 10 is visited 34 times, so 34 into 3, because 12, 20, 12, 10 all are visited when you're searching for 10, right? You start at the root node, you move to the left. So that's the cost. And here what it will be? It will be 50 into 1 plus 34 into 2. I think no, it will be 34 into 3. Actually, I've written this wrong, my bad. So it should be, it doesn't make any sense. It is not a binary search tree that I created. So it will be 10, and on the right child it will be 12. So 34. Okay, so it will be, now it will become 50 into 1 plus 34 into 2 plus 8 into 3, right? So these are all possible ways. Now it's pretty clear to us, if you compare these values, definitely this one looks much lesser than the other. Here we have 50 into 1, 34 into 2, 8 into 3. If you see the rest, they are definitely more than this value, whatever you get out of this. So this is the most optimal way you can actually have the binary search tree, right? This is the most optimal way or minimum cost, right? So you want to have the binary search tree like this. All these are possible ways you can create the binary search tree, but you want to have this one because this will give you the minimum cost. So this is the question. Is it clear with everyone? The question. Is this clear with everyone? How is this working? How is this working? Like how we are fixing this one as the minimum cost, or what is the cost? How we are computing the cost, and why does it make sense to have it like this? Is these things clear? Are these things clear? Let me know if it is clear with you. Let me know in the chat if it is clear with you guys, or is there some problem? Clear. Okay. It's clear with Chirag. That's great. Others, you can also let me know if it's clear with you guys. Let's clear everything, right? How do we solve this, right? How do we solve this? Let's come to the interesting part. Now I wouldn't say there is no other solution, so there are some greedy solutions actually that you can do, right? You can basically try formula, like you can basically try creating the binary search tree in a greedy way. Maximum frequency should come at the top, and like that, and it might work in most of the cases. Like there's already some papers that are created by Nath, and where he has actually proposed some greedy solutions, and you can definitely try that. But please explain very shortly. Okay, so the problem is basically you have to create a binary. Okay, so you have to create an optimal binary search tree. You are given some keys and you are given some frequency, so you have to minimize the cost. The cost being that what is the level of the node into the number of times it is searched for. For example, 10 and 12, you have the keys 10 and 12. So 10 and 12, like this, you can create a binary search tree. 12 and 10, this is how you can create another binary search tree. Both of them are valid, right? But you have cost. 10 is called 34 times, like you are searching for 10 34 times, you are searching for 12 50 times. So the cost will be, see, in this case, 10 is visited one times. Whenever you are searching for 10, you are directly starting at the root, it is visited one times. For searching for 12, we are visiting it two times, so the cost will be 34 into 1 plus 15 to 2. Similarly for here, 12 is visited one time, 10 is visited two times while searching for 10, so it will be 15 into 1 plus 34 into 2. So this is the optimal, so we have to do it like this. Yes, Chirag, actually you can actually try doing that. It might work for smaller test cases, but again, like it's an approximate algorithm. We cannot be sure that it will always work. There's a paper by Nath, and you can actually look into that as well. You can look into his paper on optimal binary search tree. That's definitely a valid possible solution, but it's an approximate solution. We'll definitely go for a definitive solution, right? We don't if you look into the constraints that are allowed here, generally in the interview also the constraints will be similar, that they will be allowing you a time complexity of n cube and a space complexity of n squared. So definitely we can go for a definitive algorithm instead of going for a probabilistic algorithm, right? So let's go with the definitive algorithm. How do we do that? Okay, so first of all, let's say we are fixing a key, right? We are fixing, like, just consider any set of search keys, right? Let's say you have n search keys. Just consider a subset or a subarray of search keys, right? Just consider the subarray of search keys. You are fixing one of them out of these possible set of search keys. You are fixing one of them to be the root. You are fixing this to be the root, right? So let's say the optimal cost for this, the optimal cost to actually create a bst for this will be is given by f I comma j. F I comma j, what does it give? It gives you the minimum cost. It gives you the minimum cost to create a binary search tree using keys I to j in the index I to j. In the index I to j is the index, right? In the index I to j, if you are just using those keys and you are creating a binary search tree, if fij will give you the minimum cost to create such a binary search tree, right? So for example, let's say we have the keys as 10, 20, 30, right? So f2 comma 3, it will give you basically in the range 2 to 3, that is this range. If you are creating a binary search tree, what is the minimum cost that you can have to create a binary search tree out of them? So this is the definition of fij or f23, right? So this is the definition of fij. Now we are considering only the set of keys I to j. Now let's just think about this, that this is the ultimate set of keys. Again, what is the answer to our problem? We want the minimum cost across all possible search keys. So that will be given by f0 to n minus 1. This is the answer to our problem, right? f0 to n minus 1. We want to create a binary search tree across all possible keys. So f0 to n minus 1 will give you the minimum cost to create such a binary search tree. So this is the answer to our problem, right? Now just consider any ij, and you are keep making k the root of this, right? You are making k the root of this. So when you are considering a set of keys, you can definitely create a binary search tree out of it, right? So you are making k the root of them, root of the binary search tree that you are generating. So basically k comes at the top, and on the left hand side, and there's a right child, right? K is on the top, left child and right child. Now if you look into the problem statement, it is given that you are given a sorted array of keys. Now this is very important, right? Because when you are fixing k as the root, you know that all these that are coming before k, or that are coming before index k, this is index k basically. All the keys that are coming before index k, they are the left subtree. They will form the left subtree, right? Because all of them are lesser than the element at index k. It is sorted with respect to keys. All the elements on the right are greater than index k, and so they cannot come to the left child, right? They will always be the right child if you make this the root. They will be the left child if you make this the root. So that's clear. We have k, we have left child, we have right child, right? What is fij? How can we compute fij? So this is a binary search tree independently. If you look into left is a binary search tree independently. It will also be satisfying the binary search tree conditions. Right is also a binary search tree independently. So first of all, we have to figure out what is the minimum cost to create L. Basically, create L means using these search key 0 to L minus 1. What is the minimum cost to create a binary search tree? So what is the minimum cost to create a you tell me, right? It is you tell me what should be the minimum cost to create a binary search tree from the using the keys I to k minus 1. I to k minus 1, what is the minimum cost to create a binary search tree? Because the left subtree should be a binary search tree, the right subtree should also be a binary search tree. That's the property of a binary search tree, right? So what should be the minimum cost to create a binary search tree from these set of keys? Can anyone tell? I to k minus 1, what is the minimum cost to create a binary search tree? What is the minimum cost to create a binary search tree? Very simple, right? From I to k minus 1. See this. What is the definition? Log n. I'm not telling what is the complexity. I'm telling what is the minimum cost of a binary search tree. Okay, understand this question clearly. We have to create a binary search tree, right? So we have to create a binary search tree from a given set of keys. You are given a set of keys, right? You have to create a binary search tree. Now you are telling, yes, exactly. You are telling that the kth element is the root. You are telling that the kth element is the root here. So kth element is the root here. So you have a left subtree, you have a right subtree in a binary search tree. The left subtree should also be a binary search tree. The right subtree should also be a binary search tree. And then you are combining them with k. Now k, these keys are sorted, right? So the left subtree will only contain 0 to k minus 1. The right subtree will only contain k plus 1 to the remaining j. So as the keys are sorted, so on the left only the smaller elements come, on the right the larger elements come. So what is the minimum cost to create the left subtree? Minimum cost to create a binary search tree out of the left subtree. It is f I to k minus 1, right? F I to j will give you the minimum cost to create a BST using the keys from I to j, index I to j. So you want to create a BST from the index from index I to k minus 1. What is the minimum cost? F I to k minus 1. This is the minimum cost. Similarly, what is the minimum cost to create the right subtree? The minimum cost to create the right subtree will be k plus 1 to j, right? So minimum cost for the left subtree, this is the right subtree, right? Now we have to find what is the minimum cost. We have to find Fij, right? What is the minimum cost to create a binary search tree like this? What is the minimum cost to create a binary search tree like this? K will be at the middle, at the root. L will be on the left, R will be on the right. We know the minimum cost to create L is f of I k minus 1. Minimum cost to create R is f of k plus 1 to j. What is the minimum cost to create this entire tree? Right? So it is f of I k minus the left cost to create left plus cost to create right plus whatever is the total cost available to make this left subtree the left child and this right child subtree the right child. So that will be the total cost. So what is the cost to make, and also this to be the root. So the total cost to make this the left child, how much? See, everything, all the elements on the left subtree, when we were computing f of I k minus 1, we assumed that the left subtree was the main subtree. It was the main tree. It was rooted at the root of the left subtree, right? But now all the elements of the left subtree are increasing by a level of 1. To understand this, let's assume we have 10, 20, 30, right? We have 10, 20, 30. Now we have computed for 10, right? 10 is the left child, let's say 20 is the k, right? 20 is the middle element. So we have computed for the left child and the right child the costs, right? So it will be frequency of 10 and it will be frequency of 30. Now we are to combine them like this. 20 will become the root and 10 and 30. Now the level of 10 is increasing by 1, right? Level of 10 is increasing by 1. So the whatever is the value we should add again, because all the elements in this left subtree, their levels are increasing by 1. So basically all their values will be added again, right? Or all their frequencies will be added again. So it will add frequency, it will give a contribution of frequency of 10. This will give a frequency of 30 as contribution, all the elements in the subtree of 30 rather, and this will give a frequency of 20 as contribution, because this will be the root, current root. So this will give a frequency of 20 as contribution. So the total cost will be whatever is the sum. Let's write it down here. Whatever is the sum from I to j, this entire subarray, this will be added I to j, because see, all the elements, all the frequencies are added again for all the elements, right? The frequency is added for all the elements. Let's actually take an example to understand this. So we'll do one thing. Let's take a better example maybe. So let's say 10, 20, 30, 40, right? So we are making 20 as the root. So what will be the, and let's say the frequencies are given here. Frequencies, let's take smaller values. So let's say 2, 1, 2, 3, 1, 2, something like this, right? These are the frequencies. So 20 is the key. What will be the left subtree? 10. 10 will be the left subtree. Right subtree will be 30 and 40. 30 and 40 will form the right subtree. Now what is the minimum cost to create a binary search tree out of 10? So 10's cost will be given by what? 10 will be just only one element, so the frequency only. So it will be 2. Cost will be 2 because frequency is 2. 30, 40. What are possible binary search trees against 30, 40? So 30, 40. This is a possible binary search tree. Again 40, 30. This is a possible binary search tree. Which one has the minimum cost? Let's see. So 30 is 30 into 1. This is 1 into 1 plus 2 into 2. and this is 2 into 1 plus 1 into 2. So that is 2, 3, and this is 5. So 3 is definitely better. So you will take 40, 30 like this. 40, 30, right? So this will give a binary search tree like this, 40 and 30. So the optimal is 40, 30 like this. 40, 30, and it will have a cost of how much? 3. 2 into 1 plus 1 into 1. So it will be 3. Okay, so you have the left subtree and the right subtree. Now what you are doing is you are creating 20 as the root. Left subtree is coming here, right subtree is coming like this, 40, 30. So this is the resultant tree that you are getting when you are making 20 the root. Okay, left subtree, what was the cost? The cost was 2 to create this. So definitely that will be the cost. But now if you see this 10, to visit this 10, you have to travel one more level extra because 20 is the root. So you have to travel one more level extra. We considered 10 to be the root itself, but 10 is not the root, 20 is the root, right? So you have to travel one more level extra. So 20, it will add up plus 2 more, because if you see 2 is the number of times and every time you're traveling a depth of 2, so 2 into 2 will be 4. So you have to add up plus 2 more to this. So plus 2 more. This is the left subtree value cost, right? We'll come to this part. The right subtree cost is 3. So let's write it down here, 3. Now for 40, what was the contribution here? The contribution here was 2 into 1 because you are visiting just one node. But when 20 is the root, for coming to 40, you are visiting actually 2 nodes. You are actually visiting 2 nodes, right? So the contribution of 40, that is 2, should be increased by one more time. It should be increased by one more time, right? Because you have just considered here 2 into 1. But when you are making 20 the root and you are visiting 42 times, it should be 2 into 2. So contribution of 40 is increased one more time, 2. So this is contribution of 10 is increased one more time. Contribution of 40 is increased one more time, plus 30. What did we do? For this subtree, we added 1 into 2, right? Because when this was the binary search tree, to search for 30, you needed to visit 2 nodes. But when 20 is the root, to search for 30, you have to visit 3 nodes. So you have to add the frequency again, because you are increasing its level by 1. So you have to add the frequency again here. So 1 will be added again here. That is for 30. Now if you see, this is basically the sum of this entire range, 10. And also you have to add the contribution of 20 itself. 20 is searched 3 times. So 20's contribution also has to be added. And into 1 because the level is 1. So plus 3. So if you see, this is basically the sum of this entire range, right? So the sum of the entire range plus the left plus the right. So we come to a dynamic programming solution where what is the recurrence that we get? The recurrence is f of ij. The minimum cost to create a binary search tree in the range I to j, in the subarray I to j, will be equals to, we fix one of them as the root, I to k. Let me give some space here. That's needed actually. We fix a root, so I to k minus 1 plus right subtree will be k plus 1 to j plus the sum of ij, sum of all the elements in the range I to j. Now what do we want? We want the minimum cost, right? We want the minimum cost. So minimize this over all possible values of k. So just fix one of the roots, because one of them has to be the root. One of them in this range has to be the root. Minimize these over all possible roots. So k equals to I to j. Minimize this expression over all possible roots. So is this clear with everyone? How are we getting this recurrence? And this is very similar to, if you look into the recurrence, it is very similar to the matrix chain multiplication, right? So it is a variant of the matrix chain multiplication problem. So is this clear with everyone? How are we getting the recurrence? And if you look into the complexity, you can get this range sum of a range in order of 1 time by maintaining prefix sums, right? So the total complexity will be the state complexity, that is n squared, into transition complexity, that is k is from I to j again into n. So total time complexity will be n cube. Space complexity, just the state complexity, that is n squared. So space complexity is n squared, time complexity is n cube, right? So we are getting the desired complexity as well. Is there any doubt on this? Otherwise, we can move to the code. Anyone has any doubt on this? Any doubts on this? Otherwise, we'll move to the code quickly. If you have any doubts, feel free to ask. I don't mind repeating again. I'll repeat again if you want me to. But let me know if you have any doubts. This makes sense, right? Like you are minimizing over all possible routes. Like one of these, you are finding from I to j what is the minimum BST possible. One of them will have to be the root, right? So you're fixing all possible routes and you are minimizing over one of them, minimizing over all of them, right? So, and that's why you also need to have the keys sorted. Otherwise, you cannot just consider the left child to be lesser and the right child to be greater, right? So you have to have the keys sorted as well. Is this clear with everyone? Let me know if it is not clear with you. I'll definitely repeat again. Otherwise, let's move to the code for now. I'm assuming it's clear with everyone. So let's move to the code. So I actually read a comment that keys are not sorted. So if the keys are not sorted, we have to manually sort them as well. But we'll keep that for later. Let's just focus on, like, for now, let's just focus on writing the code. So how sum is being written? Sum will take the sum as the prefix sum, right? We'll take the sum to be the prefix sum. Sum is basically the sum of all the elements in the given range. So how can you compute the sum of the range I to j? If you want the sum of the range of indices I to j, how do you compute this? You compute like this: sum of compute the prefix sum. So prefix sum of j minus prefix sum of I minus 1. I'll just increase the font size a bit, or increase the size a bit, so that it is visible to you as well. So this is how you can compute the sum, right? Prefix sum of j minus prefix I minus 1. You can keep the sums computed. Let's do one thing. Let's just to be sure that the keys are sorted. Let's just make sure that the keys are sorted. So paired intent intent frequencies, and we'll create an array of size n and we'll sort them with respect to the keys, right? So for int I equals to 0, I equals to 0, I less than n, I plus plus, frequencies of I is equals to what? It will be equals to keys of I, comma, frequency of I. So basically I want to sort them with respect to keys. So I created a paired array of pairs, right? I want them to be sorted with respect to keys. So I created a array of pairs. Or maybe I can go full screen. Yes, I created an array of pairs and then I can easily sort them, right? Because keys I is the first value, so I can easily just sort them like this: frequencies and frequencies plus n. So they are now sorted by keys, frequencies plus n. So now they are sorted by keys, right? So let's quickly compute the prefix sum. So let's create a prefix sum array of n, and p of 0 will be what? It will be equals to frequencies. It's a big name, right? So let's write it as f. Let's write it as f because we will be using it a lot. So let's write it as f and f plus n. So prefix sum frequencies of 0 dot second, right? And also we can do one more thing, just a quick trick if you want to do this. Hash define f will be second, s will be second, because we'll be using dot second a lot, so we can just replace second by s like this: f of 0 dot s, right? And for int I equals to 1, I less than n, I plus plus, p of I equals to p of I minus 1 plus f of I dot second. So this is how you compute the prefix sum. So we have computed the prefix sum. Now let's go ahead with the dp. So dp will be n this will be the total dp array size. Let's initialize dp I comma I. So what will be dp I comma I? It is the base case, right? What will be dp I comma I? What is the definition of dp I comma I? What is the minimum cost bst that you can create using the keys I comma I? So that is using only one key. What is the minimum bst? So that will only be the root. So only the frequency will be dp of I comma I will be the frequency of I, right? So for int I equals to 0, I less than n, I plus plus, dp of I comma I will be equals to what? It will be equals to f of I dot second. It will be equals to f of I dot second, the frequency only. Now we'll go into the dp solution, and what will be returned? Let's return here as well. So our answer will be dp of 0 to n minus 1. This will be our answer. The entire range of search keys. So for int I equals to 0, I less than n, I plus plus, and for int j equals to I plus 1, j less than n, j plus plus. Okay, dpij, right? We are computing dpij, so we'll fix one of them as the root. So for int k equals to I, k less than equal to j, k plus plus, one of them is fixed as the root. Now left sum, left subtree. So left subtree, how much will be the cost for left subtree? It will be equals to, if k is greater than I, in that case it will be dp I to k minus 1, or otherwise it will be 0. Similarly, what is the right subtree cost? This basically means we don't have a left subtree. 0 means we don't have a left subtree. This, we just have a right subtree or something like that. So right subtree cost, if k is less than j, in that case dp of k plus 1 to j, otherwise it will be 0. And what is dpij now? We'll compute dpij. dp of ij equals to left subtree plus right subtree, whatever is their cost, plus what is the cost to make k the root. It will be the sum of the entire range I to j. So sum of the entire range, how can we find the sum of the range I to j? So it will be prefix sum of j minus I greater than 0. If I is greater than 0, then it will be prefix sum of I minus 1. Otherwise it will be 0, like prefix sum of j from 0 to j is basically prefix sum of j. So it will be prefix sum of I minus 1 or 0. So this will be dpij, and we'll return dp0n. So this should work. Like, I'm not sure if this is the code is correct completely. So this should work. Let's actually compile and see if we have done some mistake. Meanwhile, do you have any questions with how are we writing the code? Any doubts on how are we writing? So it's, your output is 118, expected is 180. So I'm not sure. Let's see if this works actually. Okay, we're getting wrong answer. Why? We are getting 411 here. Interesting. 1, 4, 5, 32, 34. The keys are sorted. 39, 14, 40, 14, 12. Okay. And we are getting 411 here. The output should be 224. That's interesting. Let's see what we have done wrong. But meanwhile, if you have any doubts with this, let me know. I'm not sure if the test cases are correct, but yeah, I think it should be correct here. So sort is okay. We have sorted with respect to keys. I don't think two of them will have the same key. They don't have the same key. So sort f plus n should be okay. If we don't do sort, what's the issue? Will we face any issue? That's question. N is okay. Okay, dpnn and I equals to 0, I less than n, I plus plus, dpii is equals to f of I dot second. Their frequencies, yes, their frequencies. And otherwise it will be dpij is left subtree, that is dpi k minus 1, k equals to I to j, j equals to 1, j less than n, j plus plus. We're fixing the right side as well. And Okay, I think, okay, I equals to 0, 0 0 0 1. Are we running the loop wrong? dp k plus 1, it depends on k plus 1, right? It depends, if you look into this, it depends on k plus 1. So I think we are running the loop wrong. It should run reverse way, because this will not be computed. This will not be computed. K plus 1, I think it's on the right side, right? So it's greater than I, so this should not be there. So I equals to n, and we have also not taken the minimum, right? I greater than equal to 0, I minus minus. So we also have to take the minimum as well. We haven't done that. So dpij is mean of dpij, and we also have to initialize. Okay, let me just increase the screen again. So dpij is mean of dpij. We have forgotten to take the minimum as well. So to take mean, yes, I forgot the minimum as well. And okay, so minimum of dpij comma left subtree this thing, and here I have to remove L. One more thing that we have to be sure that dpij should be initially like a big value. So dpij, let's take to be int max initially. So int max initially, and we'll initialize this to be a big value, and then we'll take the minimum across all. So let's, okay, let's just can we compile and compile on this case? I'm not sure. Can we run on a custom case? Anyone has any idea? This is working. Let's submit. Okay, it's passed all the cases, so I think it's working fine. Cool. So this is the solution. Let me know if you have any doubts with this solution. Any doubts with this solution? Did you understand how we are performing the dynamic programming? Like, definitely greedy, like the first thing that actually came to my mind as well is that we can just sort with respect to their frequencies, and then try to create a binary search tree in that order. But again, like that, that might not work in many cases, although I actually did a bit of research myself, and I saw that there are some like Nath has written a paper on that, that greedy might work and these things. Okay, this custom test case, that's good to know. But anyways, it has worked for us, so that's fine. But other than that, if you have any doubts with this, like this is how you should solve this. You should think about only a set of search keys, and then try to build the answer, right? So for a set of search keys, one of them has to be the root, so just fix it to be the root. Now for the remaining part that is not the root, the left subtree and the right subtree should also be a binary search tree. So just find the cost to create them recursively. So you find their cost to create those binary search trees. Now you have to combine them, right? So if you combine them, if you see all the elements levels are increasing by +1, so their cost, their frequency should also be increased by one more time, so plus the sum of the entire range. So that's how we are getting coming to with this thing. Let me know if it is clear with everyone, or do you have any doubts? Anyone has any doubts? In case you don't have any doubts, yes, that was the problem of the day. So for, yeah, like we'll meet again later. So today in the evening I have another stream scheduled. So if you want to learn about how to detect, like these are some random problems from Amazon interviews that I'll be solving for the next couple of days. So if you want to join, you are most welcome. Today we'll be learning about how to detect cycles, mostly about the Floyd cycle detection algorithm. So how to detect cycle in a linked list, and also how to figure out what is the point the cycle begins, right? So we'll be discussing about that. So I'm hoping that you have understood this, as you're not telling me if you have understood or if you haven't. So I'm assuming that you have. So yes, we'll meet you at 6 p.m. Do join there as well. We'll be solving a few questions, and thank you and bye.